honor and also a great pleasure to come here. I really like to come here and talk to you. I consider it almost home here, so thank you very much. Today I'm going to talk about hybrid vehicles, but I would like to talk about this subject in a broader perspective, because it really is linked to several other subjects that in a first glance you can think that they are not related. So I really think it's important to look at this subject in a broader perspective. This perspective, let me explain what I mean by that. When you talk about hybrid vehicles, it's linked to, for instance, different types of fuel. Tribology is the science of contact between surfaces, and very, very important storage, motors in internal combustion engine and so on. Transportation is the broader subject, and energy mix. So this subject is so entangled, intertwined, multi-branched subject that I really gave up trying to devise a linear narrative to talk about this subject. So I decided not to do that, and I see this subject as a tree of knowledge. So every time you see a tree like this during the presentation, it means that I'm taking one or a few steps back and trying to talk to another subject. Okay, so I start my talk by explaining why it seems a mess. Okay, I'm going to talk a little bit about all these subjects during the presentation, and I'm giving up doing this in a linear way. Okay, so that's the point. And we can start by almost here at the tree trunk by talking about the energy mix. This is the United States energy mix, and I chose that one in particular because it's quite representative of the world's energy mix. We here in Brazil, our mix is quite different actually, so that's why I'm using this one as an example and as a representation of the world's mix. And you can see that in this corner, this is a Sankey diagram. In this corner you can see the sources, solar, hydro, natural gas, coal, and so on. On the right end here, you see the final applications, okay? And in the middle, you can see what we can call energy carriers. So, for instance, when you talk about electricity, okay, so electricity is the carrier, energy carrier, okay? And you see what are the sources, the main sources that contribute to generation of electricity. You see that it's mostly natural gas and coal. So if you're talking about electricity, you must understand the geopolitics of coal and natural gas and all the environmental problems and so on. Okay, and on the other end of the story, you see where electricity is being applied. So you see that well, this is a rejection of the amount of energy that is not used. I'm going to talk that in a few moments. But when you talk about the transportation sector, the main contributing source of energy is petroleum. Okay, and in between the primary source of energy and the application, you have carriers. So you have gasoline, you have ethanol, and so on. If you try to identify the contribution of electricity in the transportation sector, you can see that it's a very, very small amount. I'm not sure that you're being able to identify compared to the carriers produced from petroleum. Okay, so it's electricity. It's not very important for the transportation sector, and in addition, this is not mainly not for self-propelled vehicles. This is trains, for instance, and subways. Okay, not self-propelled. Yeah, that's the point. So when you talk about transportation, the main source of energy is petroleum. So the geopolitics of petroleum is very important for the sector. If something happens in the Strait of Hormuz, for instance, it's going to affect the whole world. Okay. So that's it. We can open up the carriers. Okay, what kinds of carriers you have here, and what types of applications you have here. You can open up this. So, for instance, you have different types of gaseous fuel, diesel, gasoline, other liquids. Ethanol is in other liquids. Okay. And electricity, a small amount of electricity. Those are the main carriers. Those are the applications. Sea, heavy road transportation like road, air, and trains, okay, railroads. And if we can choose to follow one of these carriers, for instance, gasoline, it's you see the amount that is being used is here in light road transportation, 48 exajoules. The numbers here, you have to put that in perspective. Remember, the world energy consumption is around 500 exajoules. Exa is 10 to the 18. Okay, so when talking about light transportation in roads, the essential fuel here is gasoline and a small amount of diesel, especially in Europe, and destined to transport passengers, people. Okay, so that's the point. And when you think about because this is the energy carrier, okay, that is being used to transport passengers, but you have to transform or extract the amount of energy here and to transform that into mechanical energy, especially kinetic energy, okay, because you're transporting these people here. So this is done, this is exergy actually. You can see that this mechanical energy corresponds to 30 exajoules out of 93, which is 53 plus 40, okay? The difference are labeled as losses. I don't agree with this term 100%, but the transformation of all this energy, 93 exajoules into 30 exajoules of exergy or mechanical energy, okay, is done in engines, okay? So you have to understand how engines work. For instance, gasoline light vehicles for passengers, you usually 99% of the engines are spark engines, autocycle engines, okay? And those losses, you can think that those losses are due to a poor technology here, poor realization of this technology. That's not the case. I would say 99% or 90%, let's be a little more modest, okay, of those losses are actually due to the second law of thermodynamics. They are unavoidable, okay? So you can see how this subject is highly connected, multi-branched. I'm just giving you some examples before talking, prior to talking about hybrid cars, okay? So let's move on. So remember, every time you see a tree like this, we were near the trunk here. Now I'm getting a step further. And well, let's talk about energy efficiency in the transportation sector, but in terms of energy demand per modal, okay? What are the demands for sea transportation, okay? And also in terms of environmental costs, especially in terms of greenhouse gases. Okay, you see some very interesting numbers here. Focusing on demand per modal, you can understand this in terms of this operation envelope, which is characterized by two variables, okay? The energy cost, how much energy you're spending to transport a certain amount of passengers or freight, okay, and the velocity, okay. And the term normalized, because we're dividing those variables, the energy caused by, if I'm not wrong, by the energy demand of an average passenger. Okay, so that's the normalization that we are using. In this operation envelope, the ideal world would be to work in this region, okay? Because you're accomplishing your transportation task with a very high velocity, so you're going faster, and being in this region of the variable scale means that you're spending less energy. So this is the ideal region. And when you plot the points, you survey all the transportation technologies and you plot the points in this graph. You see, for instance, in terms of passengers, okay, those boxes are actually clouds of points, and each point represents a particular car, a particular bicycle, and airplanes. Okay, sorry for the Portuguese, I didn't have time to translate everything. Okay. So you see, when you plot the actual points, you get actual applications in this region concerning passengers. And when you plot the solutions for freight, okay, those purple clouds of points, you see that you see a tendency to spend less energy. Okay, not a tendency. Actually, this is how they become more economically competitive. Okay, so every transportation solution for freight must spend, it's more important to spend less energy than going faster. Okay, and well, remember, we said that it's important to be able to, it would be nice to be able to be here. So why we're not achieving this? Okay, you see there's a void here, except for Homer Simpson over there, there's a void there. So why is that? You see that there's a kind of a frontier over there, there's a creative frontier actually, and this reflects actually the first and second law of thermodynamics, because you cannot go at a very high velocity and spending very small amounts of energy. It's not feasible, because you have to compensate for drag, aerodynamic drag, for instance. So you're going to spend energy for that. So and you see that the most important technological solutions that are near that frontier are very big planes, very big ships, and very big trucks, actually road trains. And this is understandable, because you see, for instance, talking about, this is also for ships, but let's talk about a ship. You see, the amount of revenues that you get from a ship like this depends on the volume of the ship. Okay, so the larger the volume, the higher the revenues, and the costs associated depend on the external area of the ship, because it's related to drag. Okay, so when you increase the scale, the volume increases with the scale to the third power, okay, and the area, the scale factor to the second power. So you see that by increasing the scale of your transportation vehicle, you have increasingly more volume compared with the area. So that's why for freight, especially for freight, the solutions are tending to become larger and larger and larger. And this is going to affect roads and several other aspects. So this is regarding the energy demand. Okay, when you talk about emissions, this graph here is very interesting, because you see the most highly emitting transportation model is airplane. Okay, and its consumption is not that great. It's over, where is aircraft. Okay, so you see it's only 8% in terms of energy demand, but its emissions per passenger per kilometer is several times higher than the second worst one, which are cars. Okay, and hybrid cars are here. well, except for walking and bike, the individual transportation solutions for individual transportation, you see that except for walking, bike, hybrid car is a very, very good solution here. You can see that already, okay? The other ones are collective transportation solutions, okay? And this is related to the speed at which this transportation is accomplished, because the aeronautical engines are actually optimized to be light and not to be highly efficient. So that is why developing fuel or a biofuel for airplanes, it's a very important technological challenge, because although the consumption is only 8%, the emissions are one order of magnitude higher. So you see, I'm talking about many things at the same time, so I hope you don't get lost in those. So that's why we always see the tree. So every time I'm moving from branch to branch in this tree, you're going to see this image. Okay, so let's move on and let's talk about the energy conversion chain in the transportation sector. Okay, because I talked about the primary sources. You see that it's mainly petroleum, 99% is petroleum. I don't know, ethanol, it's labeled as other fluids, and this is quite, I mean, disturbing actually for us that we are trying to develop that. And well, this is not true in Brazil. Ethanol is a very important fuel here in Brazil, but not in the world. In the world, this is incipient, I would say. Well, so let's try to make this analysis what I call the energy conversion chain, or this is also labeled from the well to the wheel analysis. Okay, so that's why you see the tree here. So let's start at the well. So you have a primary source, which we know it's petroleum. Okay, you have to transform, because petroleum is the primary source. You cannot use petroleum as petroleum in an engine, for instance. So you have to transform that into some kind of energy carrier, gasoline, ethanol, or kerosene, for instance. And when we say carrier, it means that it may be a substance, it may be a flow of electrons, for instance, electricity, but not just any type of substance or any type of flow of electrons. Okay, these substances are actually normalized. For instance, when you talk about gasoline, the viscosity is limited to a certain amount because it has to flow inside pumps and pipes of the engine. So when you talk about energy carrier, remember it's a substance or a process or a phenomenon with standardization associated. Okay, so this is very important. So to transform those primary sources into those carriers, you have to have industrial efficiency. This is very important because that's exactly what we're trying to do when we replace these petroleum wells by biomass, for instance. And remember, we have to produce a kind of a fuel which is normalized, standardized, okay? So we have to have this efficiency. It's not just a matter of knowing how to do that, but you must know how to do that with high efficiency. Okay, this is very important because otherwise it's not going to be competitive. Okay, the next step, well, gasoline is not kinetic energy. Okay, so I have to transform that into kinetic. Before kinetic energy, actually, you have to transform that into mechanical exergy. We can think about torque times rotation. That's a mechanical power in the shaft, for instance, of your propeller in your airplane, or this mechanical power in the shaft of the wheel of a car, for instance. So this is done through engines. So you have to understand how this conversion is done. And since we are talking about fuels, electricity is not the case. Okay, I'm going to talk about electricity in a moment. But you have to have thermal efficiency, and you have the second law of thermodynamics intervening in this segment. Okay, so you can have mechanical power at the level of the wheel of the propeller, for instance, of your ship, and you have also to have propulsive efficiency, because this has to be transformed into kinetic energy, which is pure exergy. So this is force times speed. In this airplane engine, for instance, you accelerate the gases in this direction, and the reaction to this becomes a force. Okay, so but this force it's not yet speed. Okay, so there are conditions at which under which this conversion or generation of speed from this force can be achieved with a high efficiency. For instance, I don't know if you know, but in order to have maximum propulsive efficiency, the speed of those exhaust gases here must be exactly the same speed as the speed of the aircraft. So that's the most efficient situation. Okay, so that's the conversion chain. Okay, primary source, fuel, mechanical exergy, and kinetic energy. Okay, and we can also segment this into self-propelled vehicles, which means that they carry its own energy source, okay, which is different from a sailboat, for instance. Its energy source is wind, and it captures the wind that is in nature. So it doesn't have to transport its own energy source. So we have to talk about energy storage technologies, okay, and also we have to talk about what we could call powertrains, the means to convert this force into speed. Okay, so tires, for instance. It's a very important subject in this matter, and it goes under the label tribology in that knowledge tree that I showed in this beginning of my talk. Okay, so this we're going to talk about self-propelled vehicles in general, and let's start by talking about energy storage solutions for these kinds of applications. So remember, I'm not talking about non-self-propelled vehicles like a sailboat or a train like this. Okay? So this is I consider this a very interesting subject, but you can start by asking yourself, how does batteries compare with liquid fuels in terms of energy storage? Okay, remember, battery stores electricity. A liquid fuel, you have to burn, you're going to produce heat, and this heat you have to convert that into mechanical energy. So the second law of thermodynamics applies in this conversion. So in order to compare fuel with batteries, you have to compare in terms of exergy, not in terms of energy. Okay, so this is fair when comparing both. If you compare the internal energy of a certain fuel, it's going to be 4 times higher, okay? Because the electricity that is stored in the battery was, for instance, produced by burning coal, and when you burn coal, you were subjected to the second law of thermodynamics. So comparing batteries with fuel in terms of what? In terms of two things. When you look for a solution for energy storage for a self-propelled application, okay, you look for 2 things, simultaneous things. You want your system, your energy storage device to be small, okay, because you have to put passengers or freight inside your vehicle, so you want to be small. And also you want it to be light, because you have to transport that together with the passengers and freight. Okay. When we plot the points related to different types and different technologies of batteries, you get these clouds that you can see here. Okay. But I want to point the scales here. You see, I don't know, the battery inside this pointer, it's probably something like one watt-hour per kilogram or something like that. Okay, when you make the calculations. So remember this scale, because we're going to see fuels, liquid fuels, in the same scale. So here are the lithium batteries, which are the most widespread batteries. It's also a geopolitic. You have geopolitics issues concerning here, because we don't have lithium all over the world. There are very few sources of lithium, and these sources are owned by few people and few groups, especially Chinese, and so you have problems when talking about batteries. Okay, but how this compare? How can you compare this with liquid fuels? When you plot liquid fuels in the same graph, you're going to see this actually. Those batteries are around this region in this graph, and you see that liquid fuels are at least 100 times more efficient in terms of mass, in terms of weight, okay, and at least 10 times more efficient in terms of volume, okay. So I would say that for self-propelled transportation applications, the only solution is liquid fuels. It's not even gaseous fuels, okay, and batteries are still is a very or an unsolved technological problem. Okay, so that's I'm preparing to talk about hybrid vehicles, because hybrid vehicles are a very natural solution to this problem. You instead of using a very large battery for an electric car, which is something like 30% of the weight of the car, you can have a very small battery, just a buffer battery, and the actual energy storage system is liquid fuel. So a hybrid car combines what? Combines the best known energy storage solution for a self-propelled application. Okay, and I didn't talk about that yet, but the electric motor is actually the best propulsion system. I'm going to talk that in a few moments. But hybrid cars are very interesting, because they combine both best solutions. Best solution for energy storage and best solution for traction, actually. Okay? So, yeah, just a few numbers, very interesting, because you can see actual points, because those are qualitative numbers, okay, except for the previous slides in which I showed you the actual numbers of batteries. But when we remember the numbers, 120, 200 watts hour per kilogram. Remember these scales. Now I'm going to show you actual fuels. You have megajoules here. It's not okay. The conversion factor is 3.6. Okay, so several orders of magnitude better. Okay, and you see, for instance, those rockets. They use this type of rocket uses two types of fuel. Okay, liquid hydrogen, for instance, for the main tank here, and solid fuel in these boosters on the side, which are in here, aluminum, things like this. You see kerosene, gasoline, diesel, and we ourselves, we're not that bad. You see the fat metabolism. So fat is a very good solution for energy storage. because we are a self-propelled transportation device. Okay, we transport ourselves, and we have to have this energy storage solution. So fat, it's a very interesting, but this is another point. Fat is a good storage system because it stores a lot of a huge amount of energy in a few kilograms, and it occupies a small volume, let's say, but the rate of release of this energy is low. Okay, I mean the power, because this is energy, not power. So that means that we are not a very we are very efficient in terms of energy, but we are not very powerful. Birds have to be powerful because they have to especially hummingbirds, they have to release energy at a very high rate. So its metabolism is going to evolve actually to take that into account. Okay, so this is a very interesting graph, and you see batteries are zinc batteries, lithium batteries are at near the origin. So that's why I say that electric cars, pure electric cars, are actually a niche solution actually. Okay, it's a very interesting solution for very specific problems, not for a general transportation problem which we have in our world today. Okay, so let's move on. You see the tree. I'm going to just change subject. I hope at the end of my talk you will be able to form a kind of a broad picture of the subject, but you have to assemble these ideas and these discussions by yourselves. I hope to be able to make this easy for you. Okay. Well, so let's talk about these traction systems, because they are the last link in the conversion chain, which I showed you a few slides ago. Okay, so we have to understand how the mechanical shaft power, the mechanical energy that you have at the level of the shaft is transformed into kinetic energy for your transportation application. So, and we're going to focus obviously on hybrid vehicles. So let's see what is a type of hybrid vehicles. I like this one. It's a BMW concept car, actually, and by concept, it means that it was not developed to earn money, but actually to test ideas. Okay, so it has a lot of interesting ideas. So let's try to understand. Let me zoom, because I think it's going to be easier. So you recognize a hybrid car because, well, first of all, it has two types of engines. Okay, internal combustion engine here and an electric motor. These numbers are particular to this model, but they are representative. Keep in mind the nominal power of the combustion engine is 300 kilowatts, and the power of the electric motor only 15 kilowatts. Keep these numbers in mind because I'm going to explain you. So first, you see you have two types of motors. Okay. Second, you have a mechanical device which can be called a power split. In addition to a gearbox, you have a power split, which actually are, I'm going to show a picture, are planetary gears. Okay, so I'm going to explain what this kind of mechanical device does. I don't know if you ever, I imagine that you guys are from very different areas. Okay, not only mechanical engineers. So you please stop me if I'm using undecipherable language. Okay, in terms of mechanics. But you can see the power split. Also, another interesting thing that tells that a car is hybrid. You have two types of energy storage. So you have a liquid fuel tank. It could be gas, but it's not efficient. Okay. So you have a liquid fuel and usually a small battery. This battery is more like a buffer battery, not It's just to, well, I'm going to show you the topologies in a few moments, so you're going to understand.
They use lithium, sodium, sulfur.
Can be the best that they can do, actually, because the point is it's small compared with the pure electric car, because the pure electric car, it has to all 100% of the energy must be stored in the battery. So roughly 1/3 or even 50% of the weight of the car is batteries. Okay, so this is very bad for efficiency. Think about the envelope that I showed you a few slides ago. Okay, but hybrid cars is just a small battery, and I'm going to explain why it doesn't need to be a big, large battery, a heavy battery. Okay, so this is a typical hybrid car, and you also have, well, traction wheels. This is very important. For instance, let me just point out that electric motors are so good in terms of traction system because they can be miniaturized and they can be put inside the wheel. Okay, you can have 4 different motors, independent motors, which can be controlled by a computer, for instance, and you can put that into each wheel. So it's a very, very good solution in terms of a traction system. No, not an attraction. A traction system, okay? But the problem is it uses pure exergy, which actually is electricity. Okay, so the problem is how to produce this electricity. So let's move on. And again, we must choose a direction in this knowledge tree here. And let's talk about these different configurations, drive configurations. Because when we talk about hybrid cars, which actually is a kind of a mixture of a pure internal combustion engine car and a pure electric car, but this melange can be made in very different ways. Okay, so let's talk about these configurations. For instance, I'm not showing you all possible configurations. There are several, but I'm going to talk about what I consider the 2 most important ones. The serial one is a very efficient, energy efficient configuration. Actually, if you look at the right here, you have the wheels, you have the motor, and you have a small battery, what I call buffer battery. Okay, so if you look here let me make a segmentation here. Okay, so if you focus on this part of the hybrid car, this is an electric car. Okay, a pure electric car has only the motor and the battery. Point. Okay, period. And the serial configuration has actually a generator, electricity generator. For an electric car, pure electric car, the generator is the power plant, burning coal, for instance, or windmills, for instance, producing electricity. And that's why for a pure electric car, the battery has to be big. Okay. In this configuration of hybrid cars, you have a generator, which actually is an internal combustion engine, okay, which is driven by an internal combustion engine. And this engine, well, it's going to use fuel. Okay, so that's the serial configuration. It has some interesting points. It uses the best storage system, which are liquid fuels. Okay, it also uses a small stationary combustion engine. In stationary, meaning its rotation is constant, not that it's going to be fixed in one point. Okay, so in order, if you don't need to work under very different rotations, you can optimize your engine in order to be very efficient at that single rotation that the engine is going to work. It's like, well, typical for generation. And this configuration also uses the best drive solution, which are electric motors. And let me point out already that electric motors are very efficient at low speeds. Okay, at high speeds, not that much. Okay, compared with internal combustion engine. So that's the serial configuration. It's a very efficient configuration. There are already several cars in the market that uses this configuration. The other one is the parallel configuration. It's the best in terms of performance. Okay, so you see, between the wheels and the motors, you have the power split, which are actually, let me zoom here in the image. So you have this kind of a planetary gears which are able to split the power. Okay. Yeah, let's see. So those devices are gears actually, and they are very interesting because they are able to, for instance, if the wheels are demanding power, this power split can, for instance, take 70% from the internal combustion engine and 30% from the electric motor. Okay. Another thing that it can do is when braking, okay, the power split can cancel this connection here, or it's not using it, and the power split can send mechanical power to the electric generator. Okay, so it can store the braking energy. So, and this is very important in urban applications, for instance, because it can amount to 30 or 15%, depending on the traffic conditions. So 15% is 15% is it's a very good saving. Okay, so the parallel configuration. So it has two motors. Remember, the BMW motor that I showed is a parallel configuration. You recognize it because you see the power split. So it has an internal combustion engine. Remember the numbers. The power was for the BMW motor was 300 kilowatts, and the electric motor was only 15 kilowatts. Okay, 15 kilowatts. It's one order of magnitude smaller, 20 times smaller. The electric motor / generator is connected to a small battery. It's still a small battery because the main source is still going to be fuel. The advantage is that you can charge the battery externally, okay, as you need to do with this fuel reservoir, okay. And another thing to point out is that this configuration also is capable of storing the braking energy. Okay, so when braking, the power split sends the mechanical energy. The motor becomes a generator. It's just a matter of switching the connections inside. Okay, and it's going to generate electricity, and this electricity is going to be stored in this in battery. Another thing that the power split can do, for instance, if the control system detects that this battery is low, it can demand, for instance, an additional amount of energy. And this amount of energy is sufficient to the demand here from the wheels, and also to charge the battery. Okay, so you have several types of flows. You can have energy flowing from the fuel reservoir, from the battery to the wheels. You can have a flow from the fuel to the wheels and to the batteries. You have all types of different configurations. Okay.
So, Professor Paulo, concerning the serial configuration, isn't it possible to regenerate energy from braking process?
Yeah, it is. Yeah, that's why I put those two arrows on both sides.
So and the efficiency of regeneration, maybe is it similar in comparison? The comparison between the two configurations.
Yeah, sorry for that. I should have written electric motor / generator, because it's also a generator. You're right, pointing that out to me. And the efficiency is comparable, because actually it's the same system. And to transform a motor into a generator is just a matter of switching the connections inside, which can be done by electronically. Okay, no problem.
So maybe in the serial parallel configuration, when you put the numbers 300 kilowatts, 50 kilowatts, but is this level of power 300 kilowatts the maximum power?
No, for that particular car. But
as in the regime of maximum power delivered by the engine,
not at all moments.
In the city, I think it would be 10 times less.
Yeah, sure. But what I want to try to explain is why the electric motor, this motor here, is in no cases it's going to be 10 or 20 times less powerful than the other one.
The maximum.
Yeah.
The limits.
The limits. Okay. And I'm going to show that, and actually we're going to make calculations and simulations those are my last slides. I'm going to be dealing with this subject. Okay.
Thank you.
Yeah. So let me conclude this slide by pointing that this configuration combines the best quality of both drive systems. And I'm already anticipating some things that I'm going to show you in detail. The electric motor is very, in addition to being efficient, it's a very good traction system at low speeds, especially when you're starting to move. Okay, I'm going to show you that. And also another good quality in terms of performance is that the internal combustion engine is very, very good at high speeds. Not translational speed, but rotation speed, okay? Because that will depend on the gear that you're using, okay? So it combines. For instance, if you need a car which has to move in cities, in high traffic cities, and also let's say 50% of its time in roads, very good roads, for instance, this is a very good configuration, because in cities you will probably use 50% the electric motor and 50% the internal combustion engines. In road conditions, you would probably be using only the combustion engine. So you have this possibility. I'm going to show you that the electric cars are very good for cities, for urban applications, okay? But not that good for, it's also good, but the internal combustion engine is better, actually, especially if you have to have liquid fuel anyway, okay? So let's move on. Let's try to be a little more specific. And when I say that the electric motor is very good for low speed applications, let me show you why, try to explain. And to understand this, you have to look at the torque curves. Sorry for the Portuguese. I keep finding things in Portuguese, so sorry for that. You please ask me if you don't understand one of those terms in Portuguese. So that's the torque curve of the electric motor, and that's the typical torque curve of an internal combustion engine. The first thing that you see is that in electric motors you have actually almost the maximum torque at zero rotation. Okay, why is that? Because in order to have a torque or a force, actually, you only need to have electricity flowing in the coils of the motor. Okay, the car can be stopped, and if you have electricity, you're going to have a force. This is very, very good, because when you're starting the movement, you need exactly this. You need a very high torque, okay, in order to start the movement, in order to start it efficiently or quickly, okay, if you're looking for performance. Another characteristic is that its torque curve tends to decrease with the increase of the rotation of the shaft. Okay, this is another typical characteristic of an electric motor. So yeah, and let's compare this with the internal combustion engine. Another very actually bad characteristic of these kinds of motors is that its torque is zero at zero rotation. Why is that? Because in order to have a force, you have to have combustion of the fluid, of the fuel. In order to have combustion, you have to have rotation of the shaft. Okay? And if you're stopped at the side, for instance, your wheel is not moving. Okay? And if you didn't have a clutch, you wouldn't be able to start the movement. Okay? Or maybe if someone pushes the car for you, you could, but not in a normal situation. So this is a very bad characteristic of the internal combustion engines, and this is why they need clutches. Okay, this is exactly the point. It has a maximum torque at a given speed. Usually the pure internal combustion engine cars, they are developed with a flat region around the maximum torque here in order to comply with different regimes, okay, rotation regimes. This is different when we if we had a stationary engine, you could develop it to be something like this, a very high and very high torque and a very efficient at this single rotation. Okay, and this is typical of a stationary engine. This curve here is typical with this flat top here is typical of cars. Okay, because they have to work under different rotations. Okay, 2,000 RPM to 7,000 RPM. Okay, this is typical application. Yeah, so let's move on. And how does a parallel hybrid car combines these two curves? So the power split, it is able to combine these two curves with different proportions. Okay, so I'm showing you here in this graph. Well, you have the torque curve of the electric motor, the torque curve of the internal combustion engine, and here you have the generated torque curve of by the power split. Okay, so those two curves, the red one and the blue one, is let's say the combination law. Okay, so if you are at low speed, 2,000 RPMs, for instance, it's going to use 100% of the electric motor, which is written in red here. And above, let's say 5,000 RPM, 100% of the power is going to come from the internal combustion engine. In between 3,000 and 5,000, you have a linear combination of both. Okay, so and this is done by the power split, which is actually a planetary gear system. Okay, so the combined torque curve is the dream torque curve, actually, because you have maximum torque at zero rotation. This is very good for starting the movement, and you have a flat top until, well, actually, at these rotations, 100% of the power is coming from the internal combustion engine, and this curve tends to fall down here because of at this regime, the problem that starts to arise is that you cannot have enough air flowing into the combustion chamber. So that's why you have compressors, for instance, in some applications. But anyway, it's going to fall for some numbers here for high rotation speeds. Okay, but this is a very, very, very interesting torque curve. Okay, because it combines both qualities. You see, you have this flat top here from the internal combustion engine. This is very good. It means you have a high torque at high rotation speeds. This is fantastic for traveling, for instance, in a road. Okay, and you also have high torques at low rotation speeds, actually at zero rotation speed. Okay, so this is a dream rotation curve. And since we're talking about several different configurations, which is the best power transmission system? So this, in order to answer this question, we have to take a few steps back here in this knowledge tree, and let's do some comparisons. Okay, so when we talk about best, it depends in terms of what. So let's talk first about energy efficiency and emissions, energy/emissions efficiency. And let's compare that with the pure electric car. Okay, so this is a typical electric car. It's very simple when you see that. It's even simpler than I'm showing you because it doesn't need to have a gearbox, for instance. I'm going to show you that in a few moments. But this is a pure electric car. It's going to be a good technological solution if this electric energy that you have to supply externally, if this electricity is produced from renewable, or at least from sources that are not emitting greenhouse gases. Okay, so if this is a good solution, if you can generate this electricity from hydropower, for instance, which is what we have here in Brazil. Okay, but let me point out that even if you're burning coal to produce electricity, this is a good solution for urban applications, especially in very large cities like Paris. I'm going to show you, like San Francisco or Santiago, for instance, cities in which you have pollution problems. Okay, they are usually near to mountains that hinders the dispersion of these pollutants. Okay, so this is, even if you're burning coal to produce electricity, at least the CO2 that is being emitted is far away from the city, or the center of the city, for downtown. Okay, so this configuration, let's take it as a reference. The electric motor is optimized, okay, for drive. It's a very good solution for drive and braking because it can recover the braking energy. This is problematical. I already told you, talked about this, okay? And I already pointed out that the electricity, it should be produced from renewable sources, or at least sources that its CO2 emissions are low, okay? I'm pointing out this because you see, I don't know if you remember my first slide, I showed you the mix, and nuclear electricity from nuclear power plants is it's a very important in the world. Okay, not in Brazil, but in the world, yes. So this is a good solution for urban areas, especially those very big cities which have dispersion problems. But you see, batteries are still a problem. Okay, yeah. If you compare that with the serial configuration, the serial configuration is actually an electric car with its own power plant. Okay, so you transport your own power plant, and this means that you're combining the best energy storage solution, liquid fuels. Okay, you have that stationary combustion engine and the generator here. Okay, so this is the series. It combines all good solutions, and you have the same problem. If you use biofuel or some fuel from renewable source, not from petroleum, for instance, this is a very good solution also in terms of emissions. Okay, it's a good solution in terms of performance. In terms of performance, it's a good solution because at low speeds, I already talked about this, and in terms of emission, it will depend on the primary source of your fuel. please don't.
In this case, you can optimize the combustion engine to work in a better torque point,
Yeah,
so
yeah,
then only
exactly.
produce the
Yeah,
energy. You
yeah.
don't have to.
No,
Not
you have
important that curve.
top. No,
Mhm.
no, you don't. This is typical. Even small generators that we can buy at the supermarket has these characteristics. They are going to work in a very specific rotation, near a very specific rotation, and they are optimized to be highly efficient at that rotation. Okay. If by some reason you have to work outside or far away from that rotation point, it's going to be very inefficient. Okay. But yeah, that's a good thing to have. Okay. So, and the other one, the parallel configuration, well, it's the same actually. Okay. So, in addition, because the parallel configuration, if you look, because of the power split, it's a very small component, relatively small component. So it transforms the parallel configuration into, because if you look at here, okay, it's almost like a pure electric car, okay, with its own power source here. Okay, so the parallel configuration is or can be in some situations or can work as a serial configuration. Okay, in this situation here, for instance, you have power coming from the internal combustion engine and being sent to charge the battery and to the wheels. In this situation, it's working almost like a serial configuration in terms of performance. Okay. In terms of emission, well, the same applies. It will depend on the source, the primary source. So if you have some renewable fuel here, or a fuel produced from some renewable source, that's okay. And the same applies to electricity. Okay. And I'm going to show you a simulation actually, the possibility of optimizing the drive not configured, but the control here, to adapt it to different situations. Okay.
Oh, in this case, it's a hybrid system with a parallel configuration.
Yeah.
And that is plugging in this case.
Yeah, it
because
can be.
we're
Yeah, you can
because
charge
you
the
can
battery.
be
Yeah.
plugging or not.
Yeah, because if you don't, if for some reason you don't have fuel, you can plug it to the outlet and charge your battery. It's no problem. Okay. So it's a very interesting and flexible technological solution. So, but the problem is still very cost. Problems are still cost. Okay. Yeah. Again, let's take another direction in this knowledge tree. I was talking about efficiencies in terms of energy and emissions. Let's talk about performance. Okay, because when we want to go from point A to B, we have conditions to be satisfied. Okay, we don't want to go from point A to B in a year. Okay, we have expectations. So performance is a very important issue. And when we talk about performance, well, there are several conditions or operating conditions. For instance, highway conditions. It's an application very different from urban conditions. Okay, in a city you stop and you start and you stop and you have traffic jams and so on. This is very different from a highway, for instance. Okay, that you're going to spend even hours at the same regime, or not a very different regime. So, and you also, well, depending, you can be talking about competition. So you would like to have a maximum speed or maximum acceleration and so on and so forth. Okay, you need to have how to compare these technologies. So let's try to make a competition, a virtual competition based on actual data. Okay, so our competition, what's the idea? We're going to have three competitors. One with a hybrid car, okay, another one with a pure electric car. Well, remember, this is electric or a serial configuration, because remember, a serial configuration is an electric car with its own power plant. Okay, and we're going to have a traditional combustion engine car. And we're going to look to two things. The acceleration time from 0 to 200 kilometers per hour, okay, and its maximum speed. Okay. That's a virtual competition. We're going to write down the equations and we're going to simulate that, and we're going to arrive at some interesting conclusions. But this is, well, you can go to a bookstore and you see many types of comparisons like this, but there's a point that when you do these comparisons, you have to compare equivalent motors. And how do you compare, or in which conditions a hybrid configuration is equivalent to an electric configuration and to a typical combustion engine? The key word here is equivalence. Okay, how do you have this? And that's what I want to explain, because the equations I'm going to show you are very, very simple. So the idea, the most important idea here is how do you have this? So let's see. Let's start writing down some equations. Well, you see, the relation between the speed and the rotation of the wheel, it will depend on the radius here and also on the transmission relation and on the rotation of the engine. Okay, so sorry if you're if this is too trivial for you, but I was wondering if we have people from several areas, so I took the liberty of reminding you some equations. Those are very simple equations, but the point here is omega is the rotation of the engine or the motor, and omega wheel is the rotation of the wheel. They don't have to be the same. Okay, and I took an actual engine. At the time I had a Mitsubishi ASX, and that's the data sheet of the car. And I don't know if you can see here, but there are some, that's the model. I have the torque and efficiency curve here. Some important parameters here: the maximum power and the speed at which it occurs, the maximum torque also. Okay, 197 Newton meter. So I'm going to virtually build three cars equivalent to those characteristics. Okay, and another important parameters are the transmission relations for each gear. Okay, so they are all going to have the same characteristics. And I wanted to point out that this is an actual car. It's still in the market. Okay, so let's see. That's our internal combustion engine car. It's already done. Okay, because we have that in the market. So let's try to build a virtual electric and a virtual hybrid car from this, being equivalent to this car here. So let's see how it works in terms of why do we have to have gears? You see, I pointed out already that the rotation of the engine is different, or not necessarily the same as the rotation of the wheel. And why is that so? Because you see, that's the torque curve of the engine, and that's the rotation speed of the shaft. Okay, and when you apply the transmission relations, which come from the gearbox, and also there are some differentials that you have a fixed transmission relation here. But anyway, when you apply this parameter A, you see that if you are in the first gear here, okay, at 7,000 RPM, your speed is going to be only 50 kilometers per hour. Okay, so that's why you need gears. If you want to go further than 50 kilometers per hour, you have to engage the second gear, third, and fourth, and fifth gear. Okay, just sorry if this is too trivial for you. Okay, I'm very sorry for that. But yeah, okay. And when we look at, not in terms of speed, because this is the speed of the car, okay? But when we look in terms of the resulting torque available at the wheel, we have this situation. So this is the torque for the, now we have the speed, okay, here. And this is the torque at first gear, second gear, and third gear. And let me zoom here. So when we have to engage another gear, for instance, at first gear you start movement, then you feel that it's slowing down, but you see at second gear you have a higher torque. So at this moment you can manually change gear. So at this moment you can manually change gear, or if it's an automatic gear, it's going to change automatically. Okay, so that is how we change gears, and that's the resulting torque. Okay, when you accelerate from 0 to the maximum. Okay, what's going to limit the maximum speed that you can achieve here is friction forces and aerodynamic drag and so on. I'm not taking that into account here. That's a simple geometrical conversion here. Okay. So that's it for the internal combustion here. That's how the let's say the available torque at the wheel when you have those gearbox and gear system. We have to have equivalent solutions for the other two competitors. Okay, the electric and the hybrid. So let's see. What are the conditions to be equivalent? If you get a general torque curve, you have, let's say, three or some important points. The maximum torque, let's say 200 Newton meters, okay? The average torque, which is the area under this curve, okay? Proportional to the area under this curve, and the limit torque at the limit speed. Okay, so we're going to look for a motor, for an electric motor with the same maximum torque, the same average torque, and the same limit torque. Okay, so that's how the electric motor can be said to be equivalent to the internal combustion engine. Okay.
And that would result in the same average power.
Yeah. I'm going to calibrate my parameters in order to satisfy this. Okay, I'm going to show you. Okay, and well, coincidentally, there is a electric motor in the market with very, very similar, not exactly, but very similar characteristics. Okay. And of course, the hybrid one is going to be the combination of both, with some laws here, and that's, let me point out this. These modulation laws here can be changed depending on well, external conditions. This is not fixed. Okay, so that's how we can have three equivalent cars. Okay, and just to show you the numbers, this is the torque curve of the internal combustion engine. When we actually I just fit this polynomial here to, let me go back a few slides to this to this torque curve. That's the actual torque curve of this actual car. Okay, so that's the mathematical regression here, and the maximum torque and the corresponding maximum speed are given in that data sheet. Okay, the limit one at 7,000 RPM. Those are the numbers, And when we fit, well, the average torque, when we fit, when we put this, when we look for the equivalence from this typical electric motor torque, we have to calibrate this parameter here. Well, this form of the torque curve already satisfy the maximum, the limit. If you calibrate here parameter A, you're going to have the same average torque, okay? And, well, by imposing the same average torque, A becomes 141, okay? This just a calibration in order to have equivalence. Yeah, and those are the torque curve of the, let's talk about this one, the hybrid car, okay, with the same strategy of changing gears, and so that's the resulting torque curve. And this one is the resulting torque curve of the electric motor. Look, this is very interesting because you don't need to have a gearbox, okay? You don't need, because if you change gears, it's only going to get worse. Okay, so this is a very interesting advantage of the electric cars because gearboxes are heavy, they are expensive, you have to maintain them, and well, so this is a very interesting factor. But the price that you're going to pay is that your torque curve is going to fall down at high flotation speeds. Okay, that's a problem. Okay, so those are the equivalent motors, and those are our competitors. And you see, that's the hybrid car, electric. Sorry for this is the internal combustion engine, the electric car, and the hybrid car here on the right. And you see that the electric motor, if you pay attention to the resulting curve, the electric motor is used only at low speed, and that is why the power here is 20 times smaller than the power here. Okay, because you need the electric motor only at the start to accelerate, and then the internal combustion engine kicks in and provides the majority of the power. Okay, so this explains why you don't need to have a very powerful electric motor. Okay, yeah. So let's complete the model to obtain the governing equations. So I already showed you the relation between torque and rotation. Okay. Well, and the governing equation is a very simple one. It says that the force, okay, the acceleration force, which comes from the torque, okay, the torque available at the wheel, is going to be used to accelerate the car. M is the mass of the car, okay, and to compensate for the aerodynamic drag. Okay, very, very simple equation. I'm not considering other influences. This is already enough. And those numbers, S is the actual area of this particular model. That's in the data sheet. So this is the frontal area, or we also call that wetted area, 2.44 square meters. And Cx is the aerodynamic coefficient. Okay, it's also given in the data sheet. So all three cars, they have the same Cx and the same frontal area. So they will have the same drag in order to be fair in our competition.
Considering the mass you have for the electric car, batteries just for
the same
you
mass.
put the same for all.
Yeah,
okay.
the same. I forgot to say that. Yeah. So what is different? Because the right-hand side of the equation is the same for all three competitors. What is different is how this torque is related to actually here to the velocity of the car, because one has gears and the electric one doesn't have. The hybrid combines two motors actually. Okay, so the difference is on the left side of the equation. Okay, so that's the governing equation, and well, to calculate the maximum speed, at permanent regime, so this term goes to zero because things are not varying anymore. Okay, so it says that the supply torque at the wheel is going to equal to the drag force. So you can see that graphically. That's this blue curve here is this one, okay, and the orange curve is the aerodynamic drag. So you see that for the internal combustion engine, you achieve 207 kilometers per hour. The electric car, 184, and the hybrid one, 208. Okay, so well, that's one of the results that we were looking for. And the other one is the acceleration test. So we have to simulate the governing equation in time. Okay, so t here is going to vary, and we're going to apply a discretization method, which is the finite difference method. This is a very simple method. You can simulate that in a spreadsheet like Excel, for instance. Okay, so very simple. So the idea is to discretize this equation. So v, the velocity v, is going to be discretized in points. Okay, so vk stands for v at times given by k times delta t. Delta t is a small number, like I don't know, 10 seconds. Okay, so it's a very simple. So the idea is to replace the derivative of this is the acceleration actually. Okay, so dv dt is replaced by delta v delta t. Very simple. Okay, and this actually becomes a means of calculating the next velocity from the previous ones. Okay, vk. So you start by v0 here, then you calculate v1. Then v1 enables you to calculate v2 and so on. So very, very simple. This is, you can use I don't know, even a spreadsheet that you have in your cell phone to simulate these equations. Okay, no problem. So what are the results? Let me control it. Yeah. What are the results? The red curve here is sorry, the colors are mixed up. Let me see. Yeah, it's easy to recognize. It should be orange. I don't know why it's white. Okay, because the internal combustion engine car was orange. So this is the internal combustion engine car. You see that it starts with it starts very slowly because of the torque curve. That's very typical. Okay, the electric, it starts very fast and is followed by the hybrid one, because the hybrid car, the parallel hybrid car, is an electric car at low speed, or behaves as an electric car at low speeds, but the electric car starts to lose performance because the torque curve starts to fall down. The hybrid one doesn't lose performance because the internal combustion engine starts to kick in and supply the necessary power. And when you look at the internal combustion engine, it's becoming a good or high performance car at higher speeds. So it's going to pass in terms of the velocity at some point. So at the end, let's see, the electric car, sorry, the hybrid car achieves 200 kilometers per hour after 30 seconds of acceleration. Okay, the internal combustion engine, let's say 45 seconds or 44 seconds, and well, the electric one does not achieve 200. Yeah, because of the torque curve. Okay. In terms of positions, in terms of positions, because this is speed. Okay. In terms of position, after 60 seconds, so let's say the internal combustion engine is almost 200 meters behind the hybrid car. Okay. The electric car is almost 300 meters behind the hybrid car here. Okay. And let me point out some things here. Okay, before moving to what I think is my last slides. the hybrid car performs better, but it has two motors. Okay, so they are equivalent to one single motor, but it has two, and it can combine the better qualities of both motors depending on the regime. So that's kind of expected, an expected result. Okay, and another thing that I would like to point out is that the logic, the controlling logic of the power split can be altered depending if you are on, because this is not a typical situation. A competition like this is not a typical situation, just to test the concept, but it can be adapted to work in a city in which you can have regions at very low speed, but also you can have a high speed avenues, for instance, so it can be modulated. Okay. And another thing that I wanted to point out is that this slide here, I'm showing you the difference how the clutch is engaged strongly influences the result for the internal combustion engine car. So if you take longer to engage, okay, you're going to take longer to accelerate, and you can, well, arrive almost at the same distance as the electric car. And this is a problem for manual, let's say manual systems. Okay, or yeah, the automatic one is supposed to be better, supposed to be optimized. Okay, so yeah, that's the car. And let me conclude this last topic by saying that the electric drive is better at lower speed, by emphasizing this fact, although batteries are very problematic as energy storage systems. I really hope that you keep this in mind. Number two, internal combustion engines perform poorly at low speeds, but liquid fuels are very good energy storage system. There is no other better solution in terms of, especially in terms of scale, of the scale of the demand of the transportation area. Okay. And third, hybrid drive combines synergically both drives in the best storage system. That's why I'm a huge fan of hybrid cars, although they are still more expensive than the traditional ones. Okay, so that's it. Thank you very much. Sorry for taking so much of your time.
Thank you.
Thank you, Professor Paulo Seleghim, for your very nice, very enlightening presentation concerning this very important subject. So I wonder if you have questions, so we can discuss. This is an opportunity.
Let's see now. This is the internal combustion engine. That was with an automatic transmission. That's how you got the.
Yeah. I showed you the logic of changing gears, and the same is applied. Well, the electric car not because it doesn't need, but the same logic is being applied to the hybrid and to the internal combustion engine.
Do you have any sense of how like a constant velocity transmission would affect those graphs? I mean, I know that's kind of a broad question.
Yeah, I didn't make these calculations, but it could be. You know, this is not my research area. Okay, I just happen to know this because I'm a very, very huge fan of hybrid cars. Every time I go to abroad, I try to take hybrid cars, taxis, and so on, and I keep looking at how they work. So I'm a huge fan, and I made some calculations and some studies.
Very interesting.
Yeah, and but some of those questions you can, by very simple simulations which I showed you here, you can answer. Because you can change, for instance, I didn't do that, but for instance, by changing the logic, by logic I mean these, where are those? Yeah, by logic I mean these laws here, modulation laws. You can change that, and you see how this affects the performance. And you can also make other or devise other types of tests, not just an acceleration test as I showed you. Okay, you can simulate different types, but they are very simple simulation. My point is that they don't have to be very, because this equation, the governing equation, where is it? This governing equation, let me see. Yeah, this governing equation is a very, very simplistic actually. Okay, you don't have elevations and downhill and uphill. You don't have this. But they are sufficient to show you a lot of things. Okay, so my point is that even though your governing equation is a very simple one, it can already show you a lot of stuff. Okay, that when you talk with people, yeah, you see that most of the time they are speculating. Okay, speculating. Those are these simulations are. That's why I took an actual car with actual data. Okay, and I try to point out that when you do comparisons, you have to be, let's say, fair in terms of comparing equivalent things. Okay, and that's it.
As a hybrid car enthusiast, do you know how much would cost a 15 kilowatts electric motor?
No, very, very cheap actually. 15 kilowatts motor is, well, for an industrial motor, you can carry. Okay, so it's not that heavy, not that expensive. I would say in reality, because by coincidence, I happened to have bought a few time ago a motor like this, something like 2,000 reais, or even less. Even less. It will depend if it has a gear system or not.
And the power split would be expensive?
Yeah, because not the gears, because they can be produced in high quantities, but you have electronic systems and to control that. And
The electronic system would be the most expensive.
yeah, I would say so. I'm not sure, but I would say so.
Are you thinking about your project car?
Yeah, I have an old gasoline car. I'm thinking about the next few years change to a hybrid.
Yeah, well, as a rule of thumb, what you have is for a serial like the Prius one, okay, it's 70% less. You pay, let's say, 25% more for the same car when you compare with an electric combustion engine car. Okay. I don't know if I'm clear, but it's 25% more expensive. That means that if you want to buy the same car, you would pay 70% of the price. The same car, but not a hybrid one.
Okay.
Okay. Yeah. more or
Total
less.
electric.
This is a very rough estimation. Okay. But it's more or less. The serial configuration, it's much more expensive because it has a power split. It has. Okay.
And the idea would be a parallel.
It would be a parallel. So it's very good in terms of performance. It's more expensive. You see, a hybrid car, it's very good in terms of performance, and it won our competition here. And I would say that the problem is that durability, because it being a more complex system with more moving parts, with more, so the probability of something going wrong is a little bit higher, I would say. So it has to be to become more robust in time. So, but to achieve this, you have to have scale. More people using parallel configuration and experimenting all kinds of problems, which will feed back to the industries and developing materials and so on in order to make these cars more robust. Okay.
Is there also hybrid systems where they split the drive systems, where like the front wheels are driven by internal combustion and the back are driven by?
I'm not sure.
This is kind of an open question.
what I know there is that for the internal combustion engine car, you have a system that controls the amount of power being sent to each wheel, independent, or to the frontal wheels and to the
like the all-wheel drive.
Yeah. This is very interesting technology, especially in for let's say non-professional drivers, or for guys like me that when I'm driving in a road, I'm thinking of
Many things.
many things. So if you have a problem, you're not going to react properly.
Yeah.
This is a statistical truth. Okay. So if you have automatic controls that controls the power, for instance, it's going to become a lot more safer. Okay, so this is a kind of technology that is worth paying for. I can say that it saved my life at least 2 times. Yeah.
Let's see. Was this an all-wheel drive car? Or
Yeah.
It is? Okay.
Once, because I told you I had one of those cars, I don't have it anymore. And once I was near Campinas, and it was raining a lot, and a lot of water on the road, and I started to lose control, and I heard this control system acting. Yeah. When I say I heard, because it accelerated and it reduced, and I was doing nothing. I was completely lost.
I used to drive Subarus.
Uh-huh.
Bulletproof as far as the all-wheel drive, snow, rain, it's just made great system.
Yeah. If you have ice on the road, because there are some roads. I lived in France, and some days it was a very hot day, but we used to go to the mountains, and the road could be very, very good. And in a curve, for instance, you can have a small flow of water which freezes on the road. I got that once. You see, so you lose completely control. If you have those kinds of systems, it's going to, because we don't have this condition here in Brazil. We have water. I don't know how that compares to other
I think
countries.
the all-wheel drives with the hydroplaning probably helps quite a bit too.
Uh-huh. Yeah, sure.
If I were to scale down the car to a subcompact, everything would be just smaller, or the proportion of the engine would alter? Like I wouldn't need it's 10 times more powerful, the internal combustion. So if you would change it to drag a subcompact.
You see the drag there. The S in the equation is the area, so it's proportional to the square of the scale factor. So at least that term is not going to be linear when you scale down. I'm not sure the other ones, because actually I'm neglecting, for instance here, I'm neglecting transmission efficiencies here. Okay, so this parameter here is a simple geometrical transmission between geometrical transformation between the motor, the shaft, and the wheel. But so my point is that I'm not sure how this will behave when you scale down, because there are some technologies, conversion technologies, that perform better at smaller scales, and there are others that perform better at large scales. Power plants, for instance. It's better to have a very, very huge power plant because it's going to be more efficient. It's better than have one huge power plant than having 2 smaller power plants. Okay.
Further questions?
Okay.
I have some questions by my own. Concerning the energy efficiency, when you compare internal combustion engines and electric engines, what are the numbers?
Yeah, the direct comparison is not actually fair, because the internal combustion engine uses fuel. So it burns fuel, generates heat, and then this heat must be converted to mechanical power. Okay, and you have the second law. You have thermal efficiency due to the second law of thermodynamics. The electric motor uses electricity, okay, which can be converted without intrinsic limit to mechanical power. Okay, and so in order to compare these two things, it would be you should include how electricity is being generated. So you should include, for instance, the efficiency of the power plant that is generating electricity.
So I would say number that I heard somehow that the efficiency of an electric engine is about 60%, and
Yeah.
internal combustion engine 50, much less than this.
Yeah,
But-
less than 30%.
But my
28, 25.
the objective of this question concerns my interest in energy regeneration using a thermoacoustic system, which is a subject of our course, and then the source of energy for this device, for in the case of internal combustion engine, is the heat which is released by the exhausting system. So this is a very important source of energy. But if I am interested, for example, in applying this device for regeneration, to regenerate heat, a source of heat from the electric engine, how, I don't know which temperatures are involved in it. So this is another question connected to the first one.
I understand, and that is why I'm always talking about exergy, because, for instance, let's say that you have 1 billion tons of water at, let's say, 40 degrees.
Yes.
Yeah, it's a very huge amount of energy, thermal energy. But if you want to convert that to electricity, the conversion will be very inefficient. So when you convert this huge amount of thermal energy, because of the low temperature, you're going to generate a very small amount of electricity. That means that this huge amount of water has a very small energy content, exergy content. Okay. So when you talk about recovering those waste energy, which are intrinsic, because it's not possible not to waste, not to reject those amounts of energy. This is intrinsic to the second law, okay, of thermodynamics. And when you talk about recovering those energies, those waste energies, you have to consider the amount of energy that you're going to be able to recover and the cost of your device, because it may cost a lot of money just to recover 0.001% of energy.
So the any sort of temperature involved in electrical engine when it is operating?
Yeah, when you talk about efficiencies, electric motors, it depends on how you calculate efficiency. If you calculate the amount of energy, mechanical energy that you have at the shaft, and the amount of supplied electric energy, this can be 99.9%. This definition of efficiency. If you consider how this electricity was generated, well, it will depend, because if it's a windmill, for instance, it's almost the same, because you are converting exergy to exergy. Okay, wind kinetic energy to mechanical power, and then electricity. So you don't have a thermal conversion in the middle. But if the electricity is coming from a coal power plant, for instance, you're going to have this.
Okay. No, I meant the structure case.
Yeah,
of
the amount of heat that. No.
Yes, in temperature.
The maximum temperature.
Of an electric motor.
The external housing of the.
Okay.
Because
I'm
this,
not sure.
this would be a source of energy.
Yeah,
Think of.
Yeah, it can be a huge source of energy, but with a low exergy content, because
Okay.
it's low temperature. It's going to be
Low
low
temperature.
temperature. Because if the conversion efficiency of the electric motor is 99%, 1% is heat at low temperatures.
Low.
Yeah, okay. Because you cannot have high temperatures because the materials and the paints and dyes and resins and inside the electric motor does not stand. They are not.
Even conductivity will decrease with higher temperature.
Sorry, I didn't.
The conductivity will decrease,
Yeah.
so you start to
Yeah,
lose
yeah.
efficiency.
Yeah, that's it. You always have to consider temperature in the equation. Okay.
I have just one more question. I was very impressed with the amount of energy available for the liquid hydrogen in comparison to other sources. So the problem is, I think, the danger involved when you use hydrogen, and also pure hydrogen. For example, when you do the chemical reaction inside such as the combustion engines, and the problem also is how to storage.
Yeah.
How to store this, right?
Yeah, that's why in that type of rocket, when I say that because I had a slide in which I showed the space shuttle, they combine two technologies. The central tank is liquid fuel and oxidizer, okay, and hydrogen or something like that. And it's a very powerful high exergy content, but you have to have the reservoirs at high pressures, and so it's going to demand weight in terms of materials and so on. The boosters, the side boosters, are solid propellant, solid fuel, and so the oxidizer is already pre-mixed with the fuel, solid fuel. There can be aluminium powder, for instance. So it's pre-mixed, and you don't have to have a tank. Okay, so it's very light and very powerful, but you don't control the combustion. For liquid fuel, you can control the reaction by injecting more or less fuel and oxidizing. But the solid propellant, no, it starts and it's going to burn to the end. Okay, you cannot control that. So that's why it's used only to boost the rocket launch at the beginning. Okay.
Further questions?
Well, Paulo, thank you very much.
Thank you.
We can have a break now. Yes. 10 minutes, something like that, isn't it?
10 minutes.
Yes. So now we can start. Finish the class. Vamos tomar um cafezinho?
Vamos. Deixei aqui os slides.
Ah, você deixou? Legal. Que a gente posta lá no Legal. Ótimo.
Posso marcar o
Muito obrigado, Paulo.
A gente está transmitindo ainda, deixa o...
Eu acho. Você deu pausa agora, por causa do café? Ah, eu vou falar com o Flávio, de repente mantém. E aí depois você só ensina como desligar esse negócio aí, enfim, que aí... É? Não tem problema? Não, meu Deus.
Okay. Let's continue with the class of today. This is another subject. It's not a hybrid vehicle. However, it's linked to this subject because the interest is on energy regeneration and the availability and exergy are aspects involved intrinsically, and these aspects must be taken into account. Well, you can regenerate energy by means of various systems, various concepts, and this one that I will talk about is using thermoacoustics. Thermoacoustics is an interplay between acoustic oscillation and heat transfer. So both phenomena involved at the same time. There is an interaction which I will explain using this presentation and other presentations. This work was a conference article, and I did this presentation 4 years ago, and I will use some figures, some illustrations, and some equations, and in the sequence I will use other presentations. All of this material will be available to you. So, to begin, this work specifically concerns sensitivity analysis to methods, applied to methods for the evaluation of a transfer matrix or transfer matrices of thermoacoustic cores. Okay, the main word in this title is thermoacoustic. In this case, it's adjective to cores, but the subject is thermoacoustics. Thermoacoustics, that I told you, is the area, specific area of acoustics that studies this interplay that I just told you. And the interest in this phenomena, because there are various phenomena involved together, is on the design and development of better efficiencies in this interplay. Okay, the system may be used for the conversion of thermal energy into mechanical energy, and the opposite way as well. In the opposite way, you can cool a system, so you are using this device as a refrigerator, or you can also use the same device with another interest, which would be the extraction of heat from a low temperature reservoir toward a higher temperature reservoir. So if you are interested in the hot part of this system, then the same device is called heat pump. So heat pump is essentially the same device of the refrigerator. In either way, so you can classify the thermoacoustic devices in two main kinds. One is engine, the other one is refrigerator / heat pump. Well, the interest in energy regeneration or energy harvesting is using this energy, which is usually waste, to other purposes, like electric generation. Therefore, the interest in this approach to this subject, thermoacoustic, is more a concern in thermoacoustic engines and not refrigeration or refrigerator / heat pump. So our concern is on engine. So this engine is a thermal engine, therefore it works from a temperature potential, and because of this temperature potential, you can generate an acoustic field. An acoustic field is sound, and an acoustic field is essentially mechanical energy. So what's the purpose of generating acoustic field? The purpose is that once you have this mechanical energy, you can transform it into electrical energy, and electrical energy is much more easy to deal with. For example, in a internal combustion engine, the temperatures involved in the exhaustion of gases reach over 500, 700 Celsius degree, and such energy is simply lost to the atmosphere, and the temperature is not so low. So the higher the temperature, the higher the availability, and therefore you can use this potential to generate electricity. Okay, but what would be, or which would be the purpose of electric generation from the heat of the exhaustion gases? Okay, if you have this source of electric energy, you can insert this electric energy into the battery, so we can charge the battery. Okay, this seems to be good. This seems to be nice. So, what do I gain from it? Well, if you can charge the battery from this alternative source, you can dismiss the regular way that you charge the battery, and the regular way by which you charge the battery is using a small engine working in the reversed way, which is called electric generator. Okay, what is the cost of electric generator? There is energetic costs involved. That is the amount of energy that is extracted from the internal combustion engine. Therefore, this electric generator demands that the whole system turns to be less efficient. So, if you charge the battery from another source, which was simply lost, you can dismiss this load from the electric generator. As a result, the whole system becomes more efficient at, I would say, roughly, without costs. Why do I say roughly? Because it's not totally true. Why? The exhaustion gases contains energy that, even though they are at perceivable high temperature, these temperatures are very low in comparison to the temperatures involved inside the chamber of the internal combustion engines. Therefore, these are energies that must be driven outside the system, so that the system, the engine, fulfills the thermodynamic laws, as the invited professor said several times during his talk, his lecture. Okay, so if you include another subsystem in the way interacting with these exhaustion gases, you increase the impedances involved. Therefore, it makes less easy or more difficult to release this low quality energy. And therefore, somehow, it will affect the efficiency of the engine in a bad way, decreasing the thermal efficiency. However, there is another way, as I said before, an increase in thermal efficiency if you can conduct this energy to charge the battery. Therefore, there is a compromise solution to deal with, and I would say, of course, as a final result, it's worthy to make this use. Okay, so where is thermoacoustics in this discussion? Thermoacoustics is on the thermoacoustic engine applied to regenerate this waste heat energy from the exhaust gases from the internal combustion engines. This is the place where the thermoacoustic engine is applied. Okay, so for now I just said the general idea to justify the following discussion. In this following discussion, we will understand how it works, which are the principles involved in the thermoacoustic phenomena, or if you resume the whole bunch of phenomena into a singular description, then you can say thermoacoustic phenomenon, singular. Okay. This conference work was about experimental methods for evaluation of a specific part of a thermoacoustic system. So it's mostly a tool or a resource to evaluate a specific part of the thermoacoustic system, so that once you have this analytical and experimental resource developing this work, you can better design thermoacoustic system. If you can better design thermoacoustic system, that means more efficient conversion of thermal energy into electricity. This is the purpose. Research works this way. You see the final goal a little bit further, but you keep this in mind. You have to keep this in mind. And that a final goal justifies a specific development that helps to do so. Okay, so how it works and what it is in fact. The first observations were done in the Middle Age. The glass blowers were very common in Europe. What did they do? They worked with glass in hot temperatures. So the physical configuration, state of the glass in this such a high temperature is no longer solid. It's liquid, very viscous. And so you can use the resulting plasticity to make the shape. They make the shape you want, or you can work on the shape of the resulting piece of glass that you wanted to have. Okay, the thing is, the temperatures involved are very, very high. In the parts of the glass, in the regions of the glass that's no longer solid. But to access this, you have to use it in indirect ways. In this figure, you can see. Look at this figure. It seems like a musical instrument, but it's not. It's not. Here you have the hot region in contact with the heat source from coal, typically. And in the other extremity, you can touch your mouth. Therefore, it's not so hot. It's probably just warm. As a consequence, you can deduce that along this tube, there is a temperature gradient. Temperature varies along this tube. Okay, so no, it's not difficult to see the system. But what happened? What happened at this tube usually emitted sound spontaneously. So spontaneously, because of this temperature gradient, it emitted sound. So this was the first thermoacoustic engine, as it converted heat engine into mechanical energy. Sorry, thermal energy into acoustic field, which is a type of mechanical energy.
The other way exists as well, like to transform sound in other kind of energy, some
Sure.
kind of receptor.
Yes, very opportune question. I just mentioned briefly about the refrigerator / heat pump. In this case, the directions of energy flux is inverted.
Mm-hmm.
So if you place here, for example, a loudspeaker, so that to keep an acoustic field inside this system, this draw represents the piece of glass. Okay, you impose an acoustic field, and because of this imposition in a specific frequency, you can pump the heat from low temperature to high temperature. So the opposite direction works. But our interest is on harvesting thermal energy. Therefore, our interest is in thermoacoustic engine. Okay. In this figure, you can see the representation of what really happens if you reproduce such a piece of glass in such conditions. It will make sound, very loud sound, very loud sound. And the interesting thing is, even if you have a sound pressure level very intense, or very, very high, the energies involved are much less than the appearances. So you have to calculate in order to deal or achieve a good design, a proper design. You can see here the temperature gradient is not zero, and this cavity, which is a bulb, works as a spring, and the air, in this case it's air, the fluid, it must be a gas. It must be a gas because the phenomena involves variations of density, and liquid almost doesn't have variation in density. Although you can conceive a thermoacoustic device working with liquid. And I saw even a modeling for a thermoacoustic device working with solid. So even for solid, you can transmit energy by means of acoustic waves through solid media.
Does your scales get larger?
Not necessarily. Not necessarily. The frequencies involved are much different, are much higher. So you can. This work was the only work that I saw in this subject was a numerical simulation, and as far as I know, no experiment was done in this concept. I can transmit to you this article. I think it's very curious, and other articles on thermoacoustics. Okay, so how it works? Because of this geometry, you can see here much larger volume in comparison to the volume inside this tube or this waveguide. If you apply thermoacoustic nomenclature. And the general behavior because of this is that the volume in this bulb works in acoustic oscillation as a spring. It accumulates energy in elastic way. And the other part of the system, if you consider the system, the gas inside this bulb, which has in this case an open extremity. So continuing, this amount of gas inside this duct is moved in comparison to the bulb, much bigger, much important displacement. And because of this higher level of displacement, the inertial effect is more important. Therefore, you can see this system as an equivalent of a system composed of mass and spring. So inside the tube or the waveguide, you have inertance. Therefore, the mass involved is important because of acceleration, which is important because of the higher displacement. In the bulb, it's the contrary. The mass could be even larger, but the displacement of the center of gravity of this region is small. But what happens in reality is an important variation of volume because of the alternating compression and rarefaction or expansion. So what happens when you have this temperature gradient, non-zero temperature gradient, and then you have a first or the small disturbances provoked by imperfections, provoked by natural convection, because there is natural convection here. At first, when you heat up this white extremity, no sound is produced. You just have temperature gradient. But because of these small disturbances along the whole system, some of these disturbances approach the natural frequency of a system such as this one that I simplified for you, equivalent to mass and spring, or inertance and compliance. When you have such a simple system, this system likes to vibrate in its natural frequency. It's signature frequency. And the excitations involved are from a wide variety of frequencies. But the ones that approach to the natural frequencies the natural frequency in the first mode of resonance of this configuration, which depends on, which is a result of this geometry of this base, this frequency is encouraged by the temperature gradient. Why? This frequency is encouraged because once the oscillation of small amounts of gas do so in this frequency or towards this frequency, the heat transfer is enhanced. The heat transfer is promoted. Therefore, when the thermoacoustic phenomenon starts, the heat transfer from, it always occurs, from the higher temperature to the lower temperature is enhanced. As a consequence, you have this mechanical energy or acoustical work resulting from this search of the nature to make the temperature profile as much uniform as possible. So to review, if there is no thermoacoustic phenomena, the heat will be transferred from hot temperature, higher temperature, to low temperature by heat conduction along the solid walls of this device, which is made of glass. Heat convection because of the portions of fluid that under the gravity acceleration moves because of the variation of density. And there is also a third form of heat transfer, which is heat radiation, because of the radiation of electromagnetic rays. Okay, so these three forms work all the time. But because of this configuration, particular configuration, any movement caused by such disturbances that coincides with the frequency of resonance of such configuration is encouraged by the fact that such additional movement creates an additional mechanism of heat transfer from the hot source to the cold source. And as a result, you have the acoustical work. Okay? Therefore, if the geometrical configuration were different, such a phenomenon would not occur. Therefore, the heat transfers involved in the thermoacoustic phenomena happens because of the interaction between the gas and the internal surface of the solid walls along the waveguide. Why? Because along the waveguide you have the thermal potential. You have the temperature gradient non-uniform. Okay, so the whole system is a thermoacoustic engine. And just to recover, the interest in here is to generate acoustic work to produce electricity. And this means the electric generator of a vehicle, right? These are just historical works. So a few centuries ago, these phenomena were first observed, and then first investigations began by the end of the 18th century, and the first good and consistent qualitative interpretation was made by Lord Rayleigh. This scientist is very, very important, as you know, and he described the phenomena the way that I just told you. So this description is very well known for over almost 1.5 century. Okay. However, the first quantitative interpretation, consistent quantitative interpretation, was done by Nicolaus Roth, which was a Hungary scientist, engineer, and he made the first acoustic approximation of this phenomenon in an analytical form by means of differential equations in linear conditions. So he made, I forgot this, proper approximations to do so. And okay. By the end of the 70s, the beginning of the decade of the 80s, some important developments were done, and the first traveling wave engine was conceived in 1979. So what is this? What is this traveling wave? This is a different configuration if you compare with this configuration. As I will explain to you later on, this configuration corresponds to stationary wave. Stationary wave. Okay? So the thermoacoustic effect can happen in a stationary wave condition and also in the progressive or traveling wave condition. Traveling wave condition is the condition in which the pressure and velocity of each small portion of the gas work together, and it makes the interaction with the solid surface in a different way if compared to stationary wave. Okay. So here is the phenomenon. As you can see here in the left figure, this is the way, general way, that a thermal engine works. Every thermal engine, it receives an amount of heat from the heat source at a higher temperature and produces mechanical work and releases thermal energy to a cold source. Remember that if you try to cut this release of energy or rejection of energy, such an engine would not work. It just works because of this potential for the energy to flow. Otherwise, you would not receive as a gain of your system the mechanical work. So this is general for all of the engines. But how it works for a thermoacoustic system? As I showed you in the previous presentation, the previous figure, you have here inside this tube a fluid, which is a gas, and this gas interacts with these internal surfaces of this waveguide. So this is the interaction. Okay, that poses a question. Why not increase the exposure of such interaction? Why not expand this surface, how do I say, the surface available for such interaction? So how would I do so in this small how to say spaces available? You can divide this waveguide in small or thin waveguides in parallel. You can place inside this tube a porous material, so that you would have as a total, as a resulting surface of interaction, the sum of the internal surfaces of each cylindrical thin pore along this place. And one material that illustrates such an aspect is a ceramic catalyst of internal combustion engine, of this exhaustion system or exhaust system of internal combustion engine. You have this piece of ceramic, and you can see, depending on the angle that you look at it, you can see the pore, the hole, and it crosses along its axial direction. You can see hundreds of such pores. If you make a simple calculation of the total surface available because of this configuration, it's pretty much increased. So if you have in the same device much more surface available for a thermal interaction, for a thermoacoustic interaction, as a result, the extension of heat conversion into acoustical energy is increased. That's why in this figure you can see, instead of simple tube waveguide, you can place a porous material, and you can see in this illustration small waveguides, small with respect to the transversal dimensions, not the length. The length is not so small. Typically, it has a few centimeters. Depends on material, depends on pressure, it depends on the fluid involved. Anyway, this is the purpose of the porous material. And this is the region where most of the efforts of investigation in thermoacoustic devices are done. Because depending on the thermophysical properties of the material, depends on the geometries involved, you can have different performances, thermal performances of this thermoacoustic engine. Okay, in this representation, you can see a heat source that inserting heat by means of this heat exchanger. This heat exchanger combined with the other, in the opposite direction of this porous material, another heat exchange that drives the energy, exhaust energy to the atmosphere, for example, or another cold source. And because of this two flux, you keep the temperature profile non-homogeneous. And inside each one of these each pore of this porous material, you have the phenomena that I just described before in this figure of this tube. So this waveguide is the equivalent of a single pore of this porous material. Okay? As a result of this conversion of thermal energy into mechanical energy, you have the acoustic field. What is acoustic field? Acoustic field is a simple way to describe that you have acoustic pressure and acoustic velocity. Acoustic pressure. What is acoustic pressure? Acoustic pressure is an increment of pressure because of the acoustic field. So, for example, we are under atmospheric pressure, here in Campinas a little less, and the average pressure is, I would say, 1 bar. That means 10 power 5 Pascal. Okay? What would be an acoustic pressure in this unit, Pascal? A high acoustic pressure would be 1 Pascal. Therefore, 100,000 times smaller than our environmental pressure. So this is the increment of pressure that you add in the other instant of the cycle, acoustic cycle, you take away. So the oscillation, just as an
100
example,
Pascal is a high acoustic pressure increase, or one? 1 Pascal.
1 Pascal. 1 Pascal is an example of acoustic pressure in which the resulting sound pressure level you can hear pretty much well. It's loud.
It's like our voice.
More.
A lot more.
Yes, or screaming maybe. I would have to confirm exactly the proper example, but it's of this order. It's of this order. So it's a pretty loud, and it is 100,000 times smaller than the average pressure in sea level. Okay, but you can have in such configurations much higher levels of acoustic pressure inside the thermoacoustic system. Therefore, you can guess that this system is no longer open as the first example. It must be completely closed and pressurized, and the fluid is not air, is typically helium, and sometimes mixed with argon. This is because the objective of these gases is to have less losses due to viscosity and higher heat transport because of higher gas conductivity. This is the why. Okay. So in this example, I just show a piece of actually a much larger system to conform the thermoacoustic engine. That's why I put some dots here, so it's longer than this. Anyway, this is the main part. This is the part where the effort is mostly driven. Oh, this is simple thermodynamics. Okay, to illustrate, for example, this is a piece of ceramic catalyst. I have these pores which have about 1 millimeter internal dimension, and it works for a stationary wave thermoacoustic device, either refrigerator / heat pump or engine. So what happens when you have stationary wave? When you have stationary wave, you can see here in this illustration a representation of a small amount of gas. How much small? I would say 1/10 of a cubic millimeter or less, 100 times smaller than 1 cubic millimeter, just to have an idea. How did I reach to this order of volume? The interest is on thermodynamic aspect, because if you're concerned with a smaller system, then you can no longer represent the system by classical thermodynamics, which requires the assumption of microscopic behavior. If you go further smaller, then you have to deal with statistical thermodynamics. Okay. Well, anyway, this is a very small portion of, but you would be able to almost see, just to give an idea. Here this particle is represented in blue to correspond a low temperature, in the opposite direction red. Okay. Remember, at first the whole system inside each small channel, which is a pore, you have a continuum variation of temperature. If there is no thermoacoustic effect or phenomenon, this temperature profile is kept this way. Nothing happens. Nothing happens further than the normal heat transport processes that I just told you before: conduction, convection, radiation. Only these three. However, because of the disturbances that are always present, so a small portion of air, for example, is displaced somehow, which corresponds to a similar oscillation in an harmonic way that approaches to the frequency of interest of the system, or resonant frequency of resonance. Then what happens? This gas particle or gas particle, we can say this way as well, oscillates left, right, left, right. But why? Why it oscillates? It doesn't oscillate for free. It oscillates because it is encouraged to do so. Encouraged by whom? It's encouraged by this plate, which is this very small wall, in this case a small ceramic wall of the internal pore of this porous material. So it oscillates, and what moves this oscillation is from the heat part of this wall, the heat transfer in the direction of this gas particle. So it takes this amount of heat and then goes to the left and makes an expansion. And when it makes an expansion, because of this expansion, the temperature gets lower, but not so lower as this wall. It is still hotter than this wall. And then energy is transferred in the reversed way, but you can see in different places when you compare to the other extremity. And because of this, the fact of this movement is harmonic, it takes more time in the extreme positions than in the middle positions. So the heat transfer is more important in the extreme positions. So it works like a piston in the thermal internal combustion engines.
So these are like micro convection cells.
Micro?
Convection cells. Like we got like why heat rises in a room and you get an effect.
No.
No.
Because this is convection phenomena. Yes,
Or like
of
if
course.
you have two plates and you get like a convection cell between them.
Yes, this is natural convection that you are talking about. But this movement is promoted by gravity, difference of density under gravity field.
Okay.
In this case, gravity doesn't play here. Does not play here.
Because the scales are so small.
No, because the phenomenon that moves this gas particle is a thermoacoustic phenomenon. This is the way. Because the frequency of movement here is the frequency of resonance of a much bigger system, which takes, for example, this size. When this movement, in principle, is aleatory, any frequency, any way, not harmonic, it happens, but it does not continue. But when it coincides with the resonant frequency of the chamber, then in this frequency the movement is encouraged. And it is encouraged because of the temperature difference that searches for another way to transport energy from the high temperature to the low temperature. That's why nature finds a way. So this is another way to do the heat transfer, a force mechanism. That's why. So nature wants to make everything most uniform as possible. So as a consequence, you gain acoustical work. And then you can make use of this acoustical work to produce electricity. So this is the mechanism.
So the sound, like the sound of the glass, when the glass blowers are blowing the glass, the sound that they hear is literally these little parcels.
Yes, but
and then you're getting a sound wave set up in the
exactly. But this interaction, this piece of glass, happens only in the internal surface of just one waveguide. And here we have many waveguides, small waveguides. Of course, the dimensions involved are not aleatory. This is designed according to the frequencies involved, in accordance with the dimensions of the whole device. I was going to tell you, okay, but in the case of the piece of glass, the extremity is open, so you hear the sound produced because of this phenomenon, because it's open. But if the system is closed, it's difficult to hear it. And interested in keeping this device closed in a very controlled chamber is the possibility of having different gases besides air, and also having a higher level of pressures. For example, 30 atmospheres average pressure, not acoustic pressure. And besides, you can have acoustic pressures involved in much higher levels than this example that I just told you a few minutes ago. So this is an initial idea that we are going to talk about. Of course, there are many things that we want to pay attention, and we are going to place this discussion in the interest of energy regeneration. But anyway, this initial idea is it precedes the following discussions. Okay, did you understand? I think I could explain reasonably.
How do you harvest power from it? Do you have like an electromagnet on the end, or like?
Yes, just a loudspeaker working in the opposite way, just like this. But for example, how a loudspeaker works? You introduce electricity, and it moves. Because of this movement, you generate an acoustic field. However, if it's not turned on, then the acoustic field reaches this membrane and make it move. When it moves, because of the coils, it generates electricity. If you pick a loudspeaker and move it with your finger, you are generating electricity.
Mm-hmm.
Because it is the opposite way to.
How much power are we talking? Like for a system like this? I mean, what's the potential, I guess?
It varies pretty much. For example, 100 watts. or bigger system, 30 kilowatts.
Okay. And the 100 watt system, what kind of footprint? How big? The unit itself.
For 1,000 watts, it's like more than a meter length, and it's not straight, and it's kind of heavy.
Okay.
Maybe 100 kilo. It depends. It depends. It varies pretty much.
The membrane can be exactly the same of the speaker, or you
speaker.
have better membranes for harvesting
Yes,
energy.
yes. It's much more like a piston of a alternating. An alternating engine, but it works in the same principle of an electrodynamic loudspeaker. In the same way, it's a coil, a magnetic core moving in axial direction.
And you just have one pickup for all the tubes, or do you have more than one?
One pickup for the tubes.
One.
Yes, just otherwise it would be
You'd be
crazy.
crazy.
Nice thinking. Okay, further question?
Usually ceramic tubes?
Depends on the kind of wave. For example, for a standing wave, ceramic porous material is pretty good. For a traveling wave, it's usually done by an environment of screens of stainless steel. So it's in the pores, the side of the pores involved are much smaller because of the thermodynamics principle is different because of the traveling wave. So it doesn't work in such a way that I just told you.
This
here.
is standing wave with the
Yes,
okay.
standing wave. Standing wave because the way the gas parcel moves is always the same.
Just
That
right
means
there, and
you receive heat from the right side. And then further on,
And just sits there.
you deliver heat in the left side. You keep this order. And because of this order, because of the fact that this order is kept this way, with time, how to say, it will necessarily correspond to the direction of the temperature profile gradient. Okay, this only happens when you have a standing wave, and this is why this movement is encouraged. It is encouraged when it coincides with the resonance frequency of resonance of the chamber. So it depends on the size of the chamber.
Okay. What kind of frequencies are we talking? Like,
Oh, slow.
I mean, you can hear
100, yes, 100, 400, for example. Even for traveling waves, 40 hertz. For standing wave, 100 or 300, 400 hertz. If the system is smaller, then the frequencies get higher. Anyway, we are able to hear for a healthy young man or woman, 20 hertz, from the range from 20 hertz to 20 kilohertz. But once you get in the 20s, your hearing gets worse. Sorry, mostly for me.
Keep going.
Yeah.
I don't understand if the resonance effect increase or decrease the potential of the interaction.
No, the frequency of resonance is naturally achieved by the system, because in this frequency the heat transport is promoted. That's why nature finds this frequency of resonance, and it finds it in accordance with the internal geometry of the chamber. Because of this stationary movement arranged in this fixed order. This example, hot part in the right and cold region in the left. And therefore the gas particle always is compressed in the right and always is expanded in the left. So that to helps and to add another way to transport energy from high temperature to the low temperature, because nature looks for this. This is fine. Anyway, I will make this presentation and other materials available in the Moodle system. Okay. Further questions?
Thank you.
I'll just make control of Cleo?
Aqui.
Cleo, Tomás, Gabriel. Ok. Presente. Karen. Tatiane. Tamar. Não tá. Depois eu vou ver se tem. Pedro. Não. Alessandro, não. Thaís, não. Ah, Thaís, desculpa. Thaís Oliveira. Tainara. Steven. Nilson. Não. Bom, vocês estão de fora. Legal, gente.
Tchau, tchau.
Até quinta-feira que vem.
What kind of temperature differences? Higher is better?
Yes.
I mean, like for your example of the one kilowatt system, what's the driving temperature difference?
Temperature difference for this system. It's like 200, 300 degrees.
That's not too bad. I mean,
No, it's not so much. But there are systems where the temperature is involved, temperature difference involved is less than 100.
Okay.
Less than 100. This is
That's
interesting
nice.
because if you can work with low temperature potential, you're pretty much more able to harvest such low quality energy.
And your systems that you're interested in, are they stationary systems or systems attached to vehicles?
Usually, the traveling wave systems are better, are more efficient,
Okay.
but they are more complex, more expensive. But in general, traveling wave systems are the best.
Okay, but also for like a stationary system, like a stationary genset or like a solar heating application or something like that, I would imagine would be where this sort of system would be good.
Traveling wave systems are the best.
Are the best.
Are the best.
Very interesting topic.
However, stationary systems, they are not just forgot, because in some specific applications they are interesting because it's simplicity, compactness, and you can also work out of the resonance frequency. With a frequency, for example, for refrigerator, you can force this phenomena even though the frequency is not in the frequency of resonance.
Wow, listen, when you say like the 1 kilowatt system, this is 1 kilowatt.
We got Paulo.
This is 1 kilowatt power output, or is it 1 kilowatt like heat transfer from end to end?
1 kilowatt of acoustic power.
Acoustic power.
Yeah.
Okay.
Acoustic power. I will speak